applications of heat pump in the industry. Term heat pump is in focus for the past few years. The refrigeration cycle was invented long ago and people experimented on the refrigeration cycle to maximize the utilization of cold chill energy. Basically, what happens that in the refrigeration cycle, generally on the evaporator side, whatever cold or the low temperature is generated, it is used for some applications, for comfort conditioning, for process application. But on the condenser side, whatever energy is generated, it is dumped into the cooling tower. So this hot energy or high temperature energy, which if otherwise dumped into cooling tower, the heat pump came into the existence to basically utilize this energy. Now we will start with the basic understanding of heat pump and then move on to the application. So what is a heat pump? Please refer to the picture on the left hand side of your screen. You are looking at the two heat pumps. Now on the top half of this heat pump, the hot water is generated and the bottom half, the cold water is generated. The top half is having a condenser and bottom half is having evaporator. Heat pump operation is very much similar to the operation of any refrigerant cycle, wherein liquid refrigerant at low temperature is evaporated in the evaporator, thereby cooling the circulating liquid or air, whatever is the media for the cooling, it lowers down its temperature. The refrigerant in the form of vapor is then compressed in the compressor. High pressure, high temperature refrigerant is then condensed in condenser by injecting heat to the circulating water or air. The high pressure refrigerant is then expanded in expansion valve and this cycle continues. So heat pump system is a system that transfers thermal energy from a cooler space to a warmer space using the refrigeration cycle, moving heat in the opposite direction in which heat transfer would take place without the application of external power. If you see at the picture on the left hand side, it basically shows the basic operation of the heat pump. Here we are putting energy in the form of electrical energy, that is W input, and we get two sources of energy. One is a cold energy and one is a hot energy. So heat is taken from a low temperature region and a greater amount of heat is exposed at higher temperature. For example, suppose 1500 watt of the energy is put inside this system, then we get around 3000 watt of cold and equivalent energy and 4500 watt of equivalent hot energy. In terms of COP of heating cycle would be 4500 divided by 1500, that is 3, and COP of cooling cycle will be 3000 divided by 1500, that is 2. So if we speak about COP, generally heat pump COP is defined based on the heating cycle. So when we say that COP of the heat pump is 3, it means that the hot energy generation would be 3 times equal to the input energy. A type of heat pump. So there are different type of heat pumps available. Mainly there are 3 type of heat pumps: air to air heat pump, air to water heat pump, and water to water heat pump. Now air to air heat pumps are basically used in pharma industries to control humidity of the air, which is for the dehumidification and then heating the stem by the steam or hot water. And air to water heat pump, basically it is used for in commercial building to pre-cool the fresh air or for hot water generation for meeting the demand of the hot water for kitchen application or etc. And water to water heat pump, it is generally for generation of hot water. It is also used to improve the performance of specific equipment. In the subsequent slides, we will go into detail about each of these applications. Rather than going into the theory, I will try to explain these systems in the practical manner. So this is a air-to-air heat pump in the pharma industry. It is for the low humidity heat pump. The system requirement is 24 degrees centigrade and 40% RH. This is the room condition requirement in the pharma industry. particular heat pump is also having a pressure, which is around 6% of the total return air. This fresh air is created in a separate TFA, wherein its temperature is brought down from 32 degrees centigrade to 10 degrees centigrade. Now, these two air when mixed together, we get a 23 degrees centigrade and 42% RH as a on-coil condition in the chill water coil. The system is having two steps of dehumidification and one set of pre-cooling. The chill water coil is primarily used for pre-cooling. Then we have a DX coil, which is used for the first step of dehumidification. And then we have a two sets of a split coil, I would rather say, where further dehumidification takes place. So this uh, air, which is at 23 degrees centigrade, 42% RH, it first gets pre-cooled in the chill water coil up to 14 degrees centigrade and 75% RH. Then it passes on to the first set of dehumidification, that is on this dehumidification coil, which is nothing but the DX type of coil, wherein a compressor or ODU is there. So based on the requirement, this coil basically fancies the temperature requirement, and based on that, it basically dehumidifies the air. So if in general condition, from 14 degree, it gets cooled down to 8 degrees centigrade, and RH is increased from 75% to 95%. Then it passes on to the two sets of further dehumidification. Here, based on the temperature, the fine temperature control takes place over here, and also based on the RH requirement, this coil is operated, either one coil or both the coils or part of the coil. So if you see the coil, at the top of the coil, there is a separate DX system, and bottom of the coil, we have got another DX system. Now this top of the coil DX system is connected to one set of heating coil that is independent, and bottom of the coil, this DX coil is connected to the second set of heating coil, which is also independent system. So from this 14 degree, the temperature reduces to 8% and 95% RH. So part of the water gets drained out over here, dehumidification takes place. Then it passes on to this DS coil. The temperature at the outlet of DS coil is 6 degrees centigrade with a 95% RH. Now the energy used for the lower cooling of the air, otherwise it would have been rejected to the ODU. It is used for the heating of the air to control the RH. So if we see at the point number 7, the 35% RH is maintained by controlling the operation of either top of the coil or bottom of the coil or both of the coil. So in this way, the low humidity heat pump is being operated, can be operated in pharma. Similar type of system we have already installed in one of the pharma factories at Goa. It is operating successfully for the last 3 to 4 years. For similar type of applications, desiccant type of dehumidification system is used, in which there is a desiccant wheel over which the air is passed. This air, after passing from the dehumidification this coil, gets cooled down by the chill water coil, and then is further reheated based on the RH requirement. And to regenerate the humidification wheel, fresh air is taken and it is heated, and that fresh air is blown over the part of the dehumidification coil to regenerate the dehumidification coil. If we compare the desiccant type system, dehumidification system with the heat pump system, the chill water coil, the system which we have shown in the previous slide, would have required 35.7 TR loading. Equivalent chiller consumption would have been 28.6 kW. In both the systems, if you see, the chiller consumption and the chill water coil load remain the same. However, if we use desiccant system and there is no DX coil, only we require either electrical heating or steam heating to maintain the RH. If steam electrical heating is used, then 94 kW equivalent energy is used for heating the air. And if steam is used, then around 200 kg per hour steam is required. Now, cost of the system If we use electrical heating with chiller load, it becomes 858 rupees per hour. If we use chiller load plus steam, it becomes 619 rupees per hour. Here the electrical energy cost is around 7 rupees per unit and steam cost is around 2.1 rupees per kg. Vis-a-vis if heat pump is installed in similar operation, then chiller load remains the same. So chiller power consumption remains the same, 28.6 kW. The DX cooling and heating system would have required 25.5 TR additional load, which would have consumed 23.1 kW power. For 28.6 plus 23.1, it becomes 51.7 kW against 28.6 and 94. So roughly 122 kW vis-a-vis 52 kW power. So electrical cost would have become 361, that is 858 to 361. So reduction of around 500 rupees per hour if desiccant heat pump is used in place of desiccant type of system. This is a example which is used to basically make you understand the difference between desiccant and heat pump and where we can use a heat pump in place of desiccant system. Now coming to the second application, that is air-to-air heat pump in dryer. In a dryer, basically hot air is required to remove the moisture from the material, and that hot air is then exhausted out of the system. Fresh air is taken, it is again heated to a temperature, and the cycle continues. We had studied one mosquito coil manufacturing facility that was using agro briquette for generating hot water at 140 degrees centigrade for drying the coil. This hot water was used for generation of the hot air, and similar two lines were in operation. Now this hot water generation was having some operating problem, and that is why it was operating in an inefficient mode. Also, the pollution control board officials had visited the factory and pointed out that black smoke is emitting from the hot water generator, and it need to be tackled. Maintenance cost of the hot water generator was also high due to frequent failures of chain grate type links. So it was having a chain grate type of firing mechanism. So that was causing also a good maintenance, high maintenance. Also, briquette cost was increasing, and it was expected to increase in future. We already, all of us experienced the increase in the cost of fuel. Briquette cost, which was around 6 rupees, 7 rupees, and now shoot up to 8 rupees, 8.5 rupees per kg. Now, low temperature drying with dehumidifier is proposed, or it was proposed to install a low temperature drying with a dehumidification. What was the proposed system? We propose that the whatever exhaust air is coming out from the dryer, it will pass through a heat pump dehumidification system. Now, water from the exhaust air will be removed by the condensation, and this heat of condensation shall be used to elevate the temperature of the air to 85 degrees centigrade. Now, since air is dehumidified, earlier they were requiring 110 degrees centigrade hot air. With the dehumidified air, this temperature of 110 degree was not required, and dryer inside temperature can also be lowered from 110 to 85 degrees centigrade. We will just see the system. This is a dryer in which material was used 770 kg of moisture, having material having 39.4% moisture. Output was 495 kg having a 6% moisture. Now whatever air which was earlier exhausted is now being taken. It was at 46 degrees centigrade. It was passed through an heat exchanger where it was cooled from 46 to 33.4 degrees centigrade. Then it was passed through the first evaporator of the heat pump, wherein around 168 kg per hour of water was removed. That is, first dehumidification step 1 was taking place over here, and the temperature was reduced from 33.4 to 27.8 degrees centigrade. Then it was passed through the second set of evaporator, where further 107 kg of moisture was removed, and its temperature dropped from 27.8 to 24.3. Now this 24.3 air was passed through the heat exchanger to exchange the heat from the dryer exhaust air at 46 degrees centigrade. So this 24.3 degrees centigrade was raised to 36.9 degrees centigrade. After raising its temperature to 36.9 degrees centigrade, it was passed through a first set of condenser of the heat pump, You see there is a heat pump. There are two heat pumps here. Heat pump 1 is on the right hand side. Heat pump 2 is on the left hand side. So heat pump 1 would have consumed 77 kW and heat pump 2 would have consumed 81 kW. Heat pump 1 evaporator is used to dehumidify the air and remove 167 kg of water. And the condenser side heat is used to preheat the air from 36.9 degrees centigrade to 61 degrees centigrade. Then this air is passed through the second heat exchanger or the condenser of the second evaporate heat pump, wherein its temperature was raised from 61 degrees centigrade to 83 degrees centigrade. So this way, whatever energy was used by briquette was eliminated and 100% was energy was sourced from the heat pump system. Also, since the same dryer exhaust air is was utilized, so most of the moisture was removed in this process and dehumidification or better dehumidified air or good quality air was used in for the drying purpose. So temperature of the air was lower from 110 degrees centigrade to 85 degrees centigrade. So this is the total from thermal energy. The system was completely shifted to the electrical energy, and heat pump was utilized to humidify the air as well as to heat the air in the same cycle. Second application of heat pump is water to water heat pump. So wherein water is used on both sides of the heat pump, that is condenser side as well as evaporator side. This system is implemented in one of the chemical factories to generate the process hot water. This process hot water is used for manufacturing of the chemicals. Now, the factory was requiring 40 kg of hot water per day, and it was to be heated from 25 degrees centigrade to 85 degrees centigrade. Earlier, they were using steam for heating the water, and this steam was generated from thermic fluid heater, and from for generation of thermic fluid, coal was used as a fuel. Now, this thermic fluid generator was at a distance from the plant, which was resulting in a line losses, as well as the plant was not having a condensate recycling system. So altogether, the system was not efficient to generate the required temperature of water. So what we propose is that we propose to install a water-water heat pump, which will generate hot water 85 degrees centigrade. The cold water or the evaporator side of the energy would be returned to cooling tower basin, thereby lowering the cooling tower temperature, which will be useful for the condenser side process application. And the heat pump COP would be 2.5. If a typical schematic of the heat system, on the left hand side, we see that there is a 10 kL demineralized water storage water. Now the factory was requiring DM water for the process. So this DM water was heated from 25 degrees centigrade to 85 degrees centigrade. There is a one pump, that is hot water circulation pump. The heat pumps were installed there, each of similar capacity, identical capacity. So if you see the temperature entering the heat pump would be 25 degrees centigrade. It will return back to the tank, and this circulation continues till we reach the temperature of 85 degrees centigrade. On the other side of the heat pump, cooling water from the cooling tower basin was used at 30 degrees centigrade as in the evaporator, and 25 degrees centigrade cooling tower was returned back to the cooling tower basin. So cooling tower temperature also reduced from 30 to 25, thereby improving the cooling tower performance also. The system is having some set of controls also. So for that control, we had installed a PLC control plus control panel. The purpose of this PLC control panel was to first sense the level of the water inside this new 10 kL tank. Based on the level controller, it will allow the makeup water addition into the tank. Second thing, based on this temperature inside the tank is to be sensed by this PLC, and based on that, it should give command for the operation of heat pump 1, 2, or 3, all the heat pump or one by one heat pump. Also, if you see, the outlet of the heat pump is connected to common header, and there are two tappings going from a common header. One is going through the 10 kL tank, and other is going to a process tank. Now the PHE, which was earlier used to heat the water from 25 to 85 degrees centigrade by using steam, was kept as it is so that whenever there is any problem with the heat pump, the same system can be started and can be used to preheat the water from 25 to 85 degrees centigrade, and the production process side of the system is not affected at all. So we had installed a two solenoid valve, one on the line going to the tank and another on the line going to the PHE. So first, this solenoid valve 2 will be kept closed or in the shut-off mode, and solenoid valve 1 will be in open position, and the water circulation continues. Once the water inside the tank reaches 85 degrees centigrade and the process is having a requirement, then solenoid valve 2 will open, then solenoid valve 1 will close, and the hot water will be stored in another 10 kL tank from where it is transferred to the river and equipment. So by this method, we have ensured that the complete system operates in automatic mode. We had also taken a fencing of this 10 kL DM hot water tank to our PLC so that whenever the level drops down to a minimum level, solenoid valve 2 opens, solenoid valve 1 closes, and this system gets automatically filled to the high level. So, so by this method, elimination of or manual intervention was completely avoided, and the system was put on complete auto mode. We come to other application of water heat pump, that is brine chiller floating head control. We all have seen that the brine chillers are used in the refrigeration cycle, be it a chemical factory or pharma factory or any factory. Generally, there are number of brine chillers used for various temperature applications, -10, -20, -30 degrees centigrade. So when we carried out energy audit of one API industry of a pharma facility, we observed that 3 brine chillers, 34 TR, 36 TR, and 21 TR were operating continuously to maintain -15 degrees centigrade brine temperature in cold well. And we also studied the historical data, which showed us that the average plant demand was between 60 to 65 TR, except when plant A is operational. So this -15 degrees centigrade brine temperature required for other plants. For plant A, it was requiring -21 degrees centigrade brine temperature. So when plant A is operational, all the 3 chillers need to operate continuously to maintain -21 degrees centigrade brine temperature in cold well. So during this plant A operation, all the 3 chillers would cater to plant A requirement demand only, and they were not able to meet the requirement of other plants. The plant A requirement was established as 21 TR at -21 degrees centigrade. The present brine chiller energy consumption was 167.8 kW and capacity output was 84 TR. So again 60 to 65 TR, it was giving output 84 TR, so it was also operating on load unload position. The brine chiller was having 8 degrees centigrade in the approach in the condenser. Generally, condenser approach is around 5 degrees centigrade. Here we uh, seen it. We show that the temperature approach is 8 degrees centigrade. This 21 TR chiller, it was operating at -13.4 degrees centigrade, and output was 18.62, again 21 TR. Even though it was operating at a lower temperature, it was designed for -21 degrees centigrade, it was operating in -13.4, till its output was lower, not 21 TR but 18.62 TR, and it was consuming 40.26 kW power. The refrigerant suction temperature was -26.08 and discharge was 38.6. You see the approach in the evaporator side also, -26 to -13. So it was around 13 degrees centigrade approach on the evaporator side. Now, when the performance of this 21 TR brine chiller, it was extended to generate -21 degrees centigrade brine. The same evaporator temperature of maintain the same evaporator temperature 12.68 degrees centigrade. It would be operating at 2.22 kW per TR. Whatever heat of condenser was that it was not utilized for any hot water generation, and this heat was rejected in the cooling tower. This is the prevent system. Now we come to what we have proposed. What we propose is to install a heat pump which will generate hot water at 70 degrees centigrade. 7 brine chiller condenser would receive cold water at 25 degrees centigrade from the evaporator heat pump so as to maintain its condensing pressure at a uniform level. Thereby, the compressor power consumption will also be constant and the specific energy consumption of the compressor will come down. This 70 degrees centigrade hot water which would be generated would be used in the plant to meet its hot water requirement. Now, there are two scenarios which we have seen in the earlier slide. Brine chiller was either operated minus 21 degrees centigrade or it was operated minus 15 degrees centigrade. So let us see scenario 1 where it is operated minus 21 degrees centigrade. The selection of heat pump depends upon the floating head control to be provided. So when 25 degrees centigrade condenser water will be given to 21 TR chiller, its performance will improve and it will operate at 2.05 kW per TR. Please remember earlier it was operating at 2.72 kW per TR. Now it will operate at a improved performance of 2.05 kW per TR. And the condenser will generate 75 degrees centigrade hot water. So the saving will be 2.72 minus 2.05, that is 0.67 kW per TR. Multiplying by the TR generation, around 13 kW of power reduction will take place if we use scenario 1. Now scenario 2, when brine chiller operates at minus 15 degrees centigrade. So when brine chiller operates at minus 15 degrees centigrade brine temperature and 38 degrees centigrade water, which is a prevent case scenario, is given to its condenser, the chiller output was 17 TR and it consumed 40.26 kW power. So specific energy consumption of chiller was 2.36. This is the base case consumption for us. What will happen if we provide 25 degrees centigrade water? So when 21 TR brine chiller operates at minus 15 degrees centigrade, 25 degree water is given to condenser. The chiller output, see the increase in the chiller output from 17 TR, it started giving 20.51 chiller, 20.51 TR output at the same power consumption. So physical consumption reduces to 1.96. So what is the performance improvement? From 2.36, it came down to 1.96. That is 0.39 kW per TR or 8 kW of power reduction. In both these scenarios, the plant in the first scenario we get 132 kW of equivalent hot water generation. In scenario 2, it will get 145 kW of hot water generation at 70 degrees centigrade. So in both the scenarios, chiller performance will improve. That is step number 1. And plant will get a constant hot water temperature of 70 degrees centigrade. That is the benefit number 2. System was very simple system. This is the prevent 21 TR brine chiller, which is a condenser and evaporator and condenser. On the evaporator side, 21 degree brine is generated. It is percolated into the plant and it returns back. On the condenser side, instead of connecting the cooling water, we suggested to install a heat pump. And the evaporator side of the heat pump is to be connected to condenser side of the heat pump. And condenser of the heat pump will be connected to the plant wherein the hot water is required. So from in the evaporator side, 25 degrees centigrade water will enter the condenser of the 21 TR brine and it will then keep on circulating, thereby maintaining the constant condensing pressure in the 21 TR brine chiller. And on the condenser side of the heat pump, hot water at 70 degrees centigrade generated, which is used in the plant for meeting the hot water requirement. So here, whatever energy otherwise was dumped into the cooling tower was first used for generation of hot water, and secondly, the improvement in the brine chiller performance was also achieved by providing a constant temperature at the condenser inlet. System which can be used is a cascade type water to water heat pump. There is a brine chiller existing condenser is here. This is the heat pump and this is the hot water. So whatever low temperature energy generated, it is used in the existing brine condenser at the 15 degree centigrade inlet and 20 degree centigrade is returns to the evaporator. Evaporator would generate 70 kW equivalent of hot energy, which can be used for meeting the hot water requirement, or it can be used to preheat the boiler feed water. In this particular system, it was suggested to use it for the water temperature rise. So a 2 kL hot water tank was proposed. The feed water temperature of the boiler at 25 degree centigrade was calculated in the condenser, and the 60 degree centigrade of hot water was achieved, which was used in the plant as a boiler feed water. So the instead of 25 degree centigrade boiler feed water, it was increased to 60 degree centigrade. Now the benefit is that chiller specific and consumption reduced from 2.16 kW per TR to 1.21 kW per TR. Hot water was available at 55 to 60 degree centigrade, and heat pump COP was 3.6. So this is also one of the ways to utilize the heat pump in the factory. Another way of air to water heat pump is the hot water generation for the industrial kitchen. It was implemented in around 2012 in Mumbai. There is a kitchen in one of the large MNC organization, and they were requiring hot water, and the hot water was generated by the electrical heater. So instead of that, this heat pump was proposed, in which 650 liter per hour of water was heated from 25 degree centigrade to 55 degree centigrade, and it was stored in an insulated hot water tank. And as per requirement, it was used for a cooking vessel or for the dishwashing purpose. On the other side of the heat pump, whatever cold air was generated, it was basically used in this particular system. It was not used for any purpose. It was thrown out into ambient. But this cold water can be used to basically pre-cool the temperature inside the dining hall. In one of the hotels where I recently carried out the energy audit, similar type of heat pump is installed to meet the hot water temperature for the bathing requirement, and the cold air is used to meet the particular requirement of their office area. So this way, both the side of the energy, cold energy as well as hot energy, can be utilized. Now, earlier they were using PNG electrical heater, so we have made a comparison of savings PNG versus heat pump. Their daily requirement of 11,000 liters per day, inlet temperature 25, outer temperature of 55. So 3,30,000 kilocalorie per day was the heat load calculated. Their existing PNG consumption was 50 SCM per day. At that time, the PNG cost was 28. So the total cost per hour was 1400 rupees per hour. By installing the heat pump, electrical power consumption was only 110 kWh per day. So at the 7 rupees per unit charges, this cost came to be around 770 rupees, that is 770 rupees per hour. So 1400 straightway dropped down to 770, that is around 50% drop in the cost of the system operation. This is a simple and very useful way of utilizing the heat pump in the industrial kitchen. This is the air to water heat pump case study in a hospital. In a hospital, they already installed a 55 degree centigrade heat pump to meet their kitchen and toilet bathing purpose. Whereas the laundry was requiring 85 degree centigrade, and they were using a dedicated boiler for the generation of 85 degree centigrade hot water. They had an 80 kW capacity heat pump which was generating at 55 degree centigrade hot water. There were multiple problems in the system. First of all, for the bathing purpose, hot water was not available at appropriate temperature. what was happening that the water which was used for the bathing, it was it would get stagnant in the line pipeline since there was no circulation, and because of the no circulation, the temperature of the water would drop down because of the insulation losses. And so when the patient open the tap, they would get or they need to drain around 15 to 20 buckets of cold water before they start getting the hot water. That was the problem number one. Problem number two was that during winter season, this hospital is located in very near to the sea coastal area of the Mumbai. So during winter season, if ambient temperature would drop down, the heat pump will start operating on part load. Since heat pump will start operating on part load, the hot water temperature will also drop down. Instead of 55, they were getting 40 to 45 degrees centigrade hot water. The other side of the heat pump, one side was used for generation of hot water, and other side of the heat pump, the chill water was circulated in the TFA of the MRI area AHUs. Since chill water from exit system was supplied to TFA during winter season, MRI area AHU was affected in terms of chill water flow and temperature. Third, fourth problem was that for laundry, hot water was not available 85 degrees centigrade, hence steam need to be used for during hot water cycle, and steam condensate stored in the tank could not be reutilized because there is no possibility of using such a high temperature condensate, and it needed to be drained. So let us see how these problems can be answered. On the left hand side, you see this is the existing system. The hot water from the heat pump tank would be stored in the hot water tank at the terrace level of a G+7 building. From there, it will pass through the shaft of the various floors. There is a ring vent system at the shaft, and it will go to shaft, and from the shaft it will go to toilet of each of the patient area. Now, what we suggested them is that instead of putting this hot water directly to the hot water tank at the storage, we basically put the isolation valve and do not store water into this hot water syringe. Instead of that, you directly pass this water to the ring vent of the shaft. From each of the shaft, you bring one pipe back to the terrace and make a return ring vent and drop this pipe down to the hot water tank at the ground level. So this way, we basically utilized a ring vent type of system which eliminated the temperature dropping problem. So water will get continuously in circulation, and temperature at any point of the time, at any hour of the day, it will remain constant. So this way, the first problem of not getting the proper temperature during bathing was mitigated. Similarly, they were also having the same system on the other building, that is G+4 building. The water from the hot water tank was stored in the on the fourth floor terrace. From there, it was brought down, and by the pump, it was circulated inside the ring vent system. Whatever water which was coming from the other floor, first floor, second floor, third floor, it was also kept on circulating inside the ring vent system. And from this tank only, they had taken the tapping for kitchen requirement and for laundry requirement. So we suggested them that first of all, do not interconnect both the lines together. Whatever water is coming around from the respective floors, you put it back into the heat pump tank so that a closed loop system can be generated. So the water from the heat pump water tank was put on the terrace of the fourth floor. From the fourth floor, a dedicated pump which was already installed and was used in the before case also, it was continuously used to supply the water on first floor, second floor, and third floor. And from each of the floor, whatever water was coming out and was collected in a common header, a line was taken and it was brought back to the hot water tank. So this way, the bathing temperature problem was eliminated for the G+4 type of building. Problem two was that during winter season, as ambient temperature drops, a part load operation was creating a problem and hot water was not available at 40 to 45 or 55 degrees centigrade, or it was only available at 40 to 45 degrees centigrade. And MRI typhoid also chill water flow was affecting. So what we suggested them is that the present heat pump was having two control logics. First was that when chill water temperature reaches 6 degrees centigrade, the chiller trips. And second, when hot water temperature reaches 55 degrees centigrade, the chiller trips. So to avoid or to tackle both the problem, we suggested them to put a artificial heating system on the chill water side, which was around 54 kV electrical heater, and control it on a on-off position whenever in the extreme condition of winter. So this was supposed to be used for 10 to 15 days in a year, so that we can get the constant 55 degree centigrade hot water in our hot water tank, and the hot water side of the problem can be completely eliminated. Last problem was about laundry, where it was requiring 85 degree centigrade, so steam was used and the whatever condensate was generated, it was drained. Now, by asking them and by calculation, we came around that around 2000 liters of hot water is required per day in the laundry, and it was required in the daytime only from 8 hours to 5:30 hours in the evening. So instead of putting any additional tank, what we suggested them that on the G+7 terrace, where they were having a two 3 KL tanks, so to dedicate one tank for laundry and to dedicate one tank for kitchen. Now these tanks would need to be installed with the level control switches, and depending upon the level control, the hot water from the hot water pump, which is in continuous circulation 24/7, would be added here to maintain the level in both the tanks. This hot water was available at 55 degrees centigrade and laundry was requiring 85 degrees centigrade hot water. So we suggested them to install a solar parabola. Then this 55 degrees centigrade hot water will get circulated in the solar parabola and will be heated to 85 degrees centigrade. This 85 degrees centigrade hot water can be used in the laundry. For this purpose, two-number solar parabola was suggested. And the condensate from the laundry. Now, here it will not be condensate, or rather, I would say it is a hot water return, which will be at around 45 to 55 degrees centigrade, would be recycled back to the hot water tank. So the condensate, which was otherwise drained, was recycled back to the hot water tank. So this way, various problems in the hospital, which is otherwise installed a very good capacity heat pump system, was mitigated and was tackled. So this is the end of my presentation. Here we have seen that we can have a different type of hot water heat pump. I started with the type of heat pump that is air to air, air to water, and water to water. So air to air, first example was for humidity heat pump for pharma. Second, for the tire application. Water to water, first case study was about generation of the processed hot water at 85 degrees centigrade for a chemical factory. Second, water heat pump about brine chiller floating head control, where a heat pump would be used to maintain a constant condensing pressure in the brine condenser and also to generate the hot water as a outcome of the heat pump to meet the hot water requirement of the factory. Another example of water heat pump was about cascade system, wherein instead of 70 degree hot water, we can get a 55 to 60 degree hot water, which can be used for any process application or which can be used for preheating the boiler feed water. To water heat pump, first we show the example of industrial kitchen wherein hot water at 55 degree centigrade was generated. Second, at to water heat pump, we show that how hot water problems in the hospital, the hot water heat pump was installed, but there were several problems associated with the heat pump system. How these problems were tackled. So I stop my presentation over here.
Yeah. Yeah. Thanks, Rakesh. That was a very nice and detailed presentation, and it covered all the practical aspects for heat pump applications. I hope everyone will benefit out of it. And this recording will be available on our LinkedIn webpage uh, from tomorrow. From tomorrow, and previous recordings are also available on our LinkedIn page. Now I request you all to kindly switch on your turn on your cameras so that we can have a photograph of the attendees. Yeah, please put on your cameras, please. I think that option is not available with you.
Someone has raised the query that it is not allowing to put on the camera by the
Yeah,
system.
yeah, yeah. Let me check. Let me check. Yes, yes, yes.